Dear students, welcome to the lecture series on the topic Engineering Graphics. Today we are going to discuss about development of surfaces of solids. I am Dr. IPS Ahuja, Professor, Department of Mechanical Engineering, Punjabi University, Patiala. Now today's discussion will be about the development of a sphere. And sphere, it is a closed surface, all points of which they are equidistant from a point which is called center. So the development of a sphere, we have already discussed that this is an object which is curved on either side, that is on the top surface as well as on the bottom surface. So we cannot develop the sphere using the conventional methods of development. So an approximate method will be used in order to obtain the development of a sphere. So the approximate method, basically it is used to develop the objects of double curved or wrapped surfaces such as sphere, paraboloid, ellipsoid, hyperboloid and helicoid. So there are two methods which are used for the development of the sphere. So in the last lecture we had discussed about the zone method for making the development of a sphere, whereas today we are going to discuss about the Lune method for obtaining the development of a sphere. And in both of these methods, the surface of the sphere can be approximately developed by dividing it into number of parts. Even in the zone method we had seen that we had got the cutting planes which are going to divide this particular sphere into multiple zones over there, and these cutting planes will have the characteristic that they will be perpendicular to the vertical axis of this particular sphere. You see, this is the vertical axis of the sphere, and all these cutting planes, they are going to cut the sphere in such a way that different zones of the sphere will be cut. And using the approximation method, you see, we are going to make the development for the upper half of this hemisphere. So if we just cut it into two halves, so the upper hemisphere, the development we obtain, then for the remaining hemisphere, once again the development will be the same. So we can divide the upper hemisphere into 3 zones or even the 4 zones over there. Now the uppermost zone, it behaves like a cone. As an approximation, we are going to assume that this upper part of the cone of the sphere will be acting like a cone over there. So the development of the cone will give us the approximate development of the upper segment of the sphere. Similarly, for the lower zones, that is zone 2, 3 or 4, then we are going to assume that once again whatever zones they are obtained, so we are going to join these 2 points and these 2 points, and then once we join them, we are going to get the development of the frustum of the cone over there. You see, once again, if I join these 2 edges, so this will form a cone over there. Similarly, if I join these 2 edges also, now we will assume that this is a cone in which the upper portion has been removed and we are left with frustum of a cone. So whatever zones or segments we are getting corresponding to the upper hemisphere, so the multiple frustums of the cones, they are being developed over there. So this thing we have discussed in the previous lecture. Now in the Lune method, we are going to once again divide the surface of the sphere into number of parts. Now here the segments, they are not, you see, here we have drawn the horizontal cutting plane. So here the cutting planes will be radial over here. And another requirement of the Lune is basically that the 2 cutting planes which are going to cut this particular surface of the cone of the sphere over there. Now both of these, you see, cutting planes, they will be joining at the axis over there. So whatever segment is taken out, this segment we call as a Lune. So we can divide this particular, you see, total circumference of the sphere into 8 equal parts, into 12 equal parts, or into 16 or 24 equal parts. So depending upon how many segments we divide the sphere into, so accordingly that many number of lunes they are going to be obtained over there. And if we are able to obtain the development of one of these lunes, it may be 1 out of 8, 1 out of 12, 1 out of 16 or 1 out of 24. So depending upon how many segments we have obtained, so we'll pick up only single lune over there, and we are going to obtain the development of a single lune. So correspondingly the development of n minus 1 number of lunes will be the same over there. So this way, if we multiply the development of one lune with the number of segments, so we are going to get the total development corresponding to this particular sphere over there. So let us work out the procedure for making the development of a sphere using the Lune method. So as we have discussed, you see here we have divided this total sphere into 12 equal segments. So one segment will be giving us one lune. So if we are dividing it into 12 segments, so 12 lunes will be obtained, and we have to carry out the development of one of these lunes over there. So you can see the lune will be, it will be starting from, you see, 0 width, and as you move along to the outermost circumference over there, maximum thickness will be encountered over here. And then again as you move towards the center on the other side, so this thickness of the lune, it is going to get shorter and shorter. So at the outermost portion you are going to get the largest possible radius or width of corresponding to this particular lune. So here lune, it is the portion between two planes which contains the axis of the sphere. So these two cutting planes which are going to obtain any particular segment of this particular sphere, they should be joining at the axis point. So this segment we call as a lune. So whatever segment is removed from the sphere, so that segment will be known as a lune. So we have to divide this sphere into equal number of parts over there. So here we are going to divide this sphere into 12 lunes or the 12 segments over there, and then we are going to divide this sphere into 12 lunes in the front view, and then make the development accordingly. And we have to select one lune for the purpose of development. So let us see another some representative, you see, diagrams we have got. So once again you can check, this is one segment, one lune, second segment, second lune, third segment, third lune, and fourth segment, fourth lune. So in this case 4 lunes are lying on this side. Similarly first, second, third and fourth, so 4 lunes are lying on this side. So 8 segments we have created corresponding to this half of the sphere, that is some one hemisphere. And then on the other side again 8 will be there. So you have divided this sphere into 16 equal segments. So this is how you see the development will be obtained corresponding to any given lune. So at the end of the diameter over there, the thickness of the lune will be 0. So it starts from 0. As you move towards the perpendicular side, so you are going to get increase in the size till you reach the other point of the axis over there, that is axis perpendicular to this diameter. So at that juncture you will find that the width of this lune will be the highest, and again as you move down to the other end of the diameter, so or the axis, so once again the thickness of this lune will keep on reducing over there. So this shape, that is the true shape of this lune, we are going to work out using the Lune method for development. So again you can see the globe. So once again, whenever we are trying to show the equator and all the other things, so once again the globe has been divided into number of segments over here. So these all segments, these can be 34, 36 segments, or even more than that, 48 as well. So these are all the lunes. So we'll be developing only the development for one of these segments over there. So this is another example. So this is a solid object into which two cutting planes, so they have removed one piece, basically one sector has been removed. So corresponding to one sector, this surface, because we have cut the solid over there, that is why it is showing us that on the interior side you have the material, but we are talking about a hollow object. So in case of a hollow object, once you remove this lune, that is only the outer surface or the peel of this particular surface has been removed. So we are going to assume that the development of the outer surface of the segment we are going to work out in this case. So the procedure, it goes as it has been described over here. So please check. We are going to draw the front view of the circle or the sphere and the top view of the sphere. And we must remember, whichever side we are going to look at the sphere, whether we look at the sphere from the front or we look at the sphere from the top, or even if we look at the sphere from the side, you observe a sphere from any given angle, irrespective whether you are looking at it on HP, on VP or on profile plane. Even if you are looking at it from any angle, even in the auxiliary planes, the view obtained will be that of a circle. So this is the front view of the sphere, which will be looking like a circle, and this is the top view of the sphere. And obviously the diameter is equal to 50 millimeter. So since we are required to draw the development of a sphere with diameter 50 mm using the Lune method over there. So front view we have drawn, top view also we have drawn. Now next step is that you locate the axis point, center point we have located. O dash is the center point in the front view, while O is the center point of the axis in the top view. Next, we are required to draw the front view, and we assume that we are going to divide this into 12 equal parts. So since 12 equal parts are there, so 12 lunes will be obtained, and once 12 lunes are obtained, but the one thing we need to remember, even if 12 lunes are obtained, we have to make development for only one of those lunes over there. So one sector will be equal to 30 degree. So here how do we draw the sector? Please check. 15 degree angle we draw above this axis, and 15 degree angle we draw below this axis line, so that the total included angle for this lune or one segment of the sphere will happen to be 30 degree. 15 degree on the upper side and 15 degree on the lower side. So this is one segment that we want to develop over here, right? So this is the front view. Now if we have to divide this over here, then I want as many points as possible corresponding to this particular segment. So in order to obtain maximum points, what we are going to do, usually we are dividing the plan in 12 equal parts. So now since I am going to require more number of projections in order to obtain more appropriate shape of the lune, then what do I need? I am going to divide this half of the circle into how many parts? 16 parts. That is 8 number of segments I am going to get over here. So that 8 on this side, and if on other side I need another 8 will be there. I am dividing this circle or the top view into 16 equal parts. So since I have lune developed only on one side, so here again points on one side of the sphere I am going to draw over here. So this is one side of the circle. So only in this semicircle portion I am going to show the division in the plan. So you see 8 segments they have been worked out. So if I have to work out 8 segments, what would be the sector angle over here? Sector angle will be 22.5. So it will be 22.5 degree for each. So that 2 sectors make 45, 4 sectors make 90 degree. Similarly 4 sectors over here making another 90. So this makes it 180 degree, right? So having divided this top view of the circle or the sphere into 16 parts, so you see 8 sectors have been created. Now let me name all those parts over here. 1, 2, 3, 4, 5, 6, 7, 8 and 9. Right? So 8 sectors or 8 segments we have created, so that we should get many points onto this lune. And as many points we obtain over here, so those points they can be transferred while I am trying to make the development for this particular lune over there. So now we have divided the top view into 16 parts. So the semicircle we have divided into 8 parts. Now the projections of all these 9 points, you see, projections corresponding to all these 9 points, they will be projected in the front view, so that we can work out corresponding to these points what would be the thickness of the lune at the different positions over there. So please see, corresponding to 1 and 9. So 1 and 9 basically correspond to the two ends of the diameter or two ends of the axis over there. So corresponding to the two ends of the axis, my thickness is going to be 0, as I explained. So if you draw the vertical projector through 1 and 9, so 1 dash and 9 dash points will be obtained at the two ends of the diagonal, which are being projected as a point over here. So please check, once I draw the vertical projectors through all these points, so first point which I am going to observe corresponding to 1 and 9, it will be 1 dash and 9 dash. So these are the points which are on the extreme sides of the diameter, which is over here, right? So which is perpendicular to this. Then corresponding to the segments 2 and 8, please check, corresponding to the first sector ending, that is 2 and 8 points. Now if I draw a vertical projector, now this is going to be my thickness of the lune over there at the points 2 and 8. So corresponding to the sectors where 2 and 8 points are located, my thickness of the lune will be this much, okay? So which is represented by 2 dash and 8 dash points over here. Then corresponding to these 2 points, please check, 3 and 7. So corresponding to these 2 points 3 and 7, the thickness of the lune will be this much, that is 3 dash and 7 dash. Then corresponding to the points 4 and 6, so what would be the thickness of the lune? You see, I am bringing the projector up. So this is going to be the thickness of the lune corresponding to the points 4 and 6 as I am trying to develop this particular lune. Then finally, this is the point as I had shown you, that at the end of the radius, you see, on the other side of the axis, on the end of the circumference over there, at the point 5. So what would be the maximum thickness? So the maximum thickness will be this much. You see, these 2 points, they are going to define maximum thickness corresponding to the point number 5 over here. So you see, 9 points we had drawn over here in the top view. Now these are the widths, that is corresponding to 2 and 8. My width will be equal to distance between A dash and B dash. Then at points 3 and 7, my width of the lune will be, which is the distance between D dash and C dash over here. Similarly, corresponding to the points 4 and 6, my thickness of the lune will be distance between F dash and E dash over here. And corresponding to the point 5, that is on the other side of the axis, now my thickness would be this much, that is distance between H dash, this point, and G dash, this point. So I have known the thicknesses at different positions over there, as I am going to start from 1 and as I am going to approach point number 9 over here. So it was this diagonal, you can see, that I was talking about, diagonal number 1 to 9. So if I am looking from this side, so these points will be coinciding over here in the front view. Now how many points I have got? 9. So now I am going to draw locus lines from all these points towards left side. So you see how many locus lines I have been able to draw? 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? So this is the 0 distance. Here 2 points are there corresponding to thickness. At points 2 dash and 8 dash, again 2 points I have identified corresponding to the location 3 dash and 7 dash. Again 2 points, that is the thickness I have identified at 4 dash and 6 dash. And then again thickness I have identified corresponding to the point 5, G dash and H dash. So total 9 locus lines horizontal they have been developed, which will indicate the thickness of the lunes at different positions. Now I have obtained the thickness values over here. Now where do I plot the thicknesses? Corresponding to these locations of the points over here. So these were 9 points. You see 8 segments we had drawn and 9 points were drawn to locate how the lune would behave at these positions over there. So now I am going to draw, this is once again, you see, I am going to draw all these points over here. And what would be the distance between all these vertical lines? the distance between the vertical lines would be, please check, it is the distance of the chord length, not the arc length. Ideally it should be arc length, but in the manual drafting we are not able to measure arc length over there. So if you are using the computer or the industrial drawing you are making using some software, obviously you can measure this arc length properly, and once you measure arc length, so distance between the 2 points on the arc have to be drawn. Whereas in the manual drafting, because we are using scale, divider or compass, so we are able to measure chord length, straight line distance between point 1 and 2, 2 and 3, 3 and 4. So these will all be equal over there. So once we measure any given segment over here, so right now we are measuring the chord length, that is straight line distance between point 1 and 2. But using software, you can measure arc distance between point 1 and 2, arc length, rather than the chord length. Now I am going to mark all these points. Please check. Point number 1, point number 2, point number 3, point number 4, point number 5, point number 6, point number 7, point number 8 and point number 9. So total 8 arcs are there, 8 segments. Segment 1, segment 2, segment 3, segment 4, segment 5, segment 6, segment 7, segment 8. Right? Now I have drawn the location of all these, you see, positions over there. Right? So 9 positions they have been shown as they were indicated in the top view. At every position I know the thickness of the lune. So at point 1, what would be the thickness? Similarly at point 9, here the thickness will be 0. Here again the thickness will be 0. Corresponding to points 2 and 8, thickness will be distance between B dash and A dash. So at 2, this will be my distance. Distance between B dash and A dash over here. Similarly at point 8, my distance of the lune, thickness of the lune would be this much. Corresponding to, you see, points 3 and 7, corresponding to the points 3 and 7, my distance would be distance between D dash and C dash. So corresponding to 3, this distance would be there, starting from here, ending here. Similarly for 7, starting here, ending here. Similarly for 4 and 6, now it is second last lines on either side. So corresponding to 4 and 6, second last line is this, second last line is this. Similarly for 6, second last line, second last line. And finally at point 5, G and H. So G and H means extreme. So corresponding to point 5, extreme point, extreme point. So all these distances, vertical distances, I am going to mark on these 9 points. So let us see. Point 1, distance is 0. So I have put a dot over here. Point 2, distance was distance between B dash and A dash. That is first line from the center point on the upper side, first line below the center line. Corresponding to 3 and 7, second line from the center, second line from the center. So corresponding to point 3, the distance would be this one, second from center above, second from center below. That is which distance I am talking about? DC. Here the distance was BA. Just check. Here the distance was BA. Here the distance is DC. So here I am going to mark D. That is distance of D. That is 2, you see, blocks from the center above and 2 projection lines below the center line. What about this 4 and 6? 3 blocks from the center above, 3 blocks from the center below. That is distance of F and E over there. So same distance I will be marking. You see, first, second and third projection line. First, second and third. So this distance corresponds to F and E over there. So I have marked F and E. What about 5? Extreme points, G and H. So extreme points are G and H. So please see last projection line through G dash and through H dash. So this will be G, this will be H. So just the reverse will follow on the other side. So once again, corresponding to point 6, this will be distance FE. Corresponding to point 7, distance will be DC. So I have not repeated it because we already know that what will be the distances. Then corresponding to point 8, it will be AB. that is one projection line above the center, one projection line below the center, and finally point 9, it is lying on the center point. Now you can see the shape of the lune. So we have drawn more number of points over here, so the better accuracy of the lune could be obtained because of that. Had we divided it into 12 parts, lesser points would have been available. Had we divided this total into 8 equal parts, so very little number of points would have been available. So this is the development of one lune. So we have divided this into 12 sectors or the 12 lunes. So 12 such lune developments will give us the complete development of the sphere. So this is the Lune method that we have discussed, and you can see over here one sector has been developed, and this is the shape which we are going to obtain. Okay, so at this particular juncture over here, we are going to get the maximum thickness at these points, that is 1 and 9. The distances will be 0. So as you progress from 1 and 9 towards 5, so the width of the lune will be increasing. From 5 to 9, once again your width of the lune, it will be reducing over there, right? So this way we have been able to obtain the development of a sphere using the Lune method, and once again this is an approximation method over there. So through these discussions we have been able to evaluate how to make the development of a sphere using the zone method as well as the Lune method in this lecture as well as in the previous lecture. So this is all for today. Now we'll be proceeding with few more lectures in the forthcoming session. So thank you very much. Thanks a lot. Thank you.